in this session, we will continue with what we have seen before on the devices that are used for efficient power conversion. We had seen in some of the past sessions the devices such as the electronic switches and the inductors, which are the devices, lossless devices used for efficient power conversion. In today's session, we will look at transformers which are used in power conversion circuits for the purpose of voltage matching, impedance matching, isolation and so on. Transformers also come under the same category as electromagnetic elements, just like inductors. The transformer has an electrical circuit and also a magnetic circuit, and the electrical circuit and the magnetic circuit are coupled to each other. So, we will see in today's session some of the basic principles of operation of transformers, the electrical circuit modeling, the magnetic circuit modeling, the mathematical relationship between the different electrical quantities as well as the magnetic quantities to the geometric properties of the magnetic circuit. And then we will look at some sample specifications of a transformer, how to design such a transformer and what is the meaning of designing a transformer, how to design such a transformer and so on. And having designed, what kind of non-idealities exist in the transformers in comparison with the ideal transformer, how to quantitatively evaluate these non-ideal properties of the transformer and so on. The devices The transformers serve several purposes in the power conversion circuits, and one of them is to match voltage levels in power conversion circuits from one part of the circuit to another part of the circuit. Ideally, transformers do not store energy. This is the fundamental difference between a transformer and an inductor. We had seen in the previous session that inductors are used in power conversion circuits in order to store energy, in order to smoothen the flow of energy, which is necessary because we control the power flow using switches which are discontinuous elements. So, the basic purpose of using inductors in a power conversion circuit is to smoothen the flow of energy, and inductors have the property of storing electrical energy, and this storage of energy helps us to smoothen the flow of energy in a power converter. In comparison with the inductor, the transformer is also an electromagnetic circuit, but the fundamental difference is that they do not store energy. Ideally, the transformers do not store energy. In power converters, transformers are also used for another purpose, and that purpose is to provide electrical isolation between one part of the circuit and another part of the circuit. If you wish to transfer energy from one part of the circuit which is electrically isolated from another part of the circuit, transformers are absolutely essential in such situations. So, we see two reasons for the presence of transformers in power conversion circuit. One of them is to transform voltage levels, and the other is to isolate circuit portions or circuit parts, two parts of the circuit where we wish to transfer energy, but they have to be isolated electrically. In such cases also transformers are used. Okay. As a schematic, this is the representation of a transformer. It has two parts which normally we call as the primary and the secondary, and with the lines that are indicated here as the magnetic core, the electrical circuit primary, the electrical circuit secondary. And these primary and secondary have characteristic turns, N1 turns for the primary and N2 turns for the secondary. And from one part of the circuit, the transformer is excited with a certain voltage, and this voltage sets up a flux in the core, and the rate of change of flux determines the voltage across the winding, primary winding as well as the secondary winding. So, without any electrical connection between one part of the circuit to the other, between the primary and the secondary, through the electromagnetic coupling in the core of the magnetic transformer, energy is transferred from one part of the circuit to the other part, or from the primary to the secondary. We can transfer electrical energy through the intermediate core by the property of electromagnetic induction. Now, one of the fundamental relationships which determines the ratio of voltage on the primary to the voltage on the secondary, V1 by V2, is related to N1 by N2 by this relationship. V1 by V2 is equal to N1 by N2. This is the primary of the transformer with N1 turns. You have the secondary of the transformer with N2 turns, and both these primary and secondary are coupled to each other through a magnetic core which is part of the same circuit, and the excitation is from one part of the circuit. In this case, we call V1 as the primary, and excitation is from V1, and a secondary voltage is induced on the secondary winding which is V2, and a load can be connected across V2, and an I2 will flow through the load, and energy can transfer from this part of the circuit to that part of the circuit without having electrical connection in between. And we can transform the voltage levels by simply changing the ratio of N1 and N2. If N1 and N2 has the ratio of 1:2, then V2 will be 2 times V1. It is possible to step up the voltage on the transformer from the primary to the secondary, or if we have N1 by N2 with a ratio of 1:0.5, it is possible to step down the voltage from a higher voltage to a lower voltage. Accordingly, transformers may also be called as step up transformer or step down transformer, or you could have simply a 1:1 isolation transformer where the voltage levels are same, but electrical isolation between the primary and the secondary is provided by the transformer. So, in this particular situation, we see that the transformers can match voltage levels between V1 and V2 by appropriate selection of the ratio of number of turns. The transformers are also used for providing electrical isolation between one part of the circuit and another part of the circuit. As I had said, the primary excitation sets up in the core a certain amount of flux, and the relationship between the primary voltage and the flux follows the Faraday's law of V is N times d phi by dt, and the same flux linking the secondary winding produces a voltage which is secondary turn times the same d phi by dt, and you get a secondary voltage which is V1 times N2 by N1 with an isolation between the primary and secondary. Electrical isolation is desired in many cases for the purpose of safety from one part of the circuit to another part of the circuit. If you do not want electrical connection which may lead to hazards, in such a case isolation can be provided using transformers. The ideal property of the transformer is that it transforms energy without any loss in the transformer. Ideally, the transformer converts power with unity efficiency. Efficiency of power conversion in a transformer from the primary to the secondary is 1. There are no losses in the transformer. We might say that the primary power V1 into I1 is equal to the secondary power V2 into I2, and because of this ideal property of efficiency being 1, the turns ratio is the ratio of the voltages as well as the inverse ratio of the currents. For example, V1 by V2 is N1 by N2, and the same ratio is also I2 by I1. You would see that by cross multiplying these terms, you will find V1 I1 is V2 I2, and that is the property of lossless power transformation. So, this forward voltage conversion ratio and the reverse current conversion ratio in a transformer ideally are the same as the ratio of the number of turns. So, what you notice here is V1 by V2 is I2 by I1, which is the same as the ratio of the number of turns on the primary and the number of turns on the secondary. The circuit schematic of a transformer in many situations will be represented in this form. So, this has a dependent current source and a dependent voltage source, and the turns ratio being N1 by N2, we can indicate that V2 is a voltage source which is dependent on V1 by the conversion ratio N2 by N1, or V2 is N2 by N1 times V1. So, this is a dependent voltage source, and this voltage source, when a load is connected here, will result in a secondary current, and the secondary current will set up a dependent current source here, where I1 is N2 by N1 times I2, and so the primary current is decided by the secondary current multiplied by N2 by N1, and the secondary voltage is determined by the primary voltage multiplied by N2 by N1. These relationships are through the turns ratio transformation, and the primary and secondary can be shown as a dependent voltage source on this side and a dependent current source on this side, and this dependency is the same as the ratio of the number of turns, ratio of the secondary turns to the primary turns. V2 is N2 by N1 times V1, and I1 is N2 by N1 times I2. Physically, a transformer has a magnetic circuit and an electrical circuit. The electrical circuit in this particular situation consists of two parts, a primary, the red winding shown here, and the secondary winding shown in red color here. And the same schematic I have now shown physically through a toroidal core. The shape is not very important, we will see later. There are many preferred shapes are available. We will see from the standard data sheets the different kinds of core shapes are available. So, here I have shown schematically a magnetic circuit which a toroidal core, a ring core, and on that I have a primary winding which has N1 turns and which is being excited by a voltage V1 and drawing a current of I1. On the same core, we have the secondary winding also wound, which has N2 number of turns, and on account of the fact that they are both coupled, the primary excitation sets up a flux in the core and sets up a secondary voltage which is V2, and V2, if you connect an external load on the output side, will result in a current of I2. V2 is N2 by N1 times V1, I1 is N2 by N1 times I2. The same relationship as we have seen. We have now explicitly shown the magnetic circuit and also the windings which are wound on the magnetic circuit, so that they are coupled to each other. Okay. Now, in this I have indicated a few more quantities which will be of interest to us. The ring has a cross sectional area of AC. This is normally referred to as the core area of the transformer. The magnetic circuit has a core which is a circular cross section, and it has an area of AC millimeter square or meter square, and this core is made up of a magnetic material whose permeability is mu. This mu is the magnetic permeability of the core. Good transformers can be built with core materials which have very high permeability. The ideal transformer will have cores whose permeability is infinity, so that you will be able to set up a magnetic field in the core with minimum amount of magnetization effort. The transformer does not store energy as we have seen. So, as a result, the core material is made up of ideal magnetic material whose permeability is infinity. The core reluctance is ideally L over A mu. The reluctance core reluctance I think is marked here as infinity. We should say core permeance is infinity or core reluctance is 0. The core shape is chosen more for convenience. In this case, in order to understand the concepts, I have shown it as a ring core, but we will see later that there are other shapes available. Okay. Now, the kind of cores that we had used for inductors, E cores, are also suited for transformers. In this circuit, instead of a ring core, I have a E shape core, two pieces of E shapes. They are put against each other, so that you have a closed magnetic circuit, and in the central limb both the primary winding, the red color winding, and the secondary winding, which is the blue color winding, are wound. These other views are of the same assembly from the top and from the side. But the important point to notice is that the core does not have a gap. The core is closed and there is no air gap, and this is because the core does not store energy, and the ideal property of the core material is of high permeability, and on account of that the core reluctance has to be 0, and on account of that the flux set up in the core can be done with minimum magnetizing effort. Again, just like in the case of inductor electromagnetic circuit, there are a few interesting geometrical shapes that we try to identify here. This cross section that is shown here as the core area is the area through which the magnetic field is set up. And you see here the cross section that is shown here as a rectangular part is the window through which the winding is wound. So, the total copper conductors making the primary and the secondary are wound in the central limb, and they have to be accommodated in the window that is shown here. And the total flux in the core has to pass through this cross section, and we can say that the window AW accommodates the primary and the secondary conductors, and the core links both the primary and the secondary, and the core area supports the total flux in the magnetic circuit. The blue winding is the secondary winding, and the red winding here is the primary winding. The Faraday's relationship of the voltage and the flux in an electromagnetic circuit is given here. We see that the core links both the primary and the secondary. All the flux in the core are linking the red winding, which is the primary winding, and they are also linking the blue winding, which is the secondary winding. So, in the central limb of the magnetic circuit, we have a flux which is denoted by the symbol phi. So, we can say that the primary voltage is primary turns multiplied by the rate of change of flux in the core, and the secondary voltage is the secondary turns multiplied by the rate of change of the flux in the core. And the flux in the core is same because both primary and secondary are linking the same flux, the same limb, that is in the middle limb. The winding, primary winding is also wound round the same core, and secondary winding is also wound round the same core. So, the flux that is linking the primary winding, which is phi, is the same as the flux that is linking the secondary winding, and the primary voltage is N1 times d phi by dt, secondary voltage is N2 times d phi by dt. And this relationship immediately relates to the property that we have seen, that V1 by V2 is same as N1 by N2, because the flux in the core is same, common for both of them. Supposing if we excite such a magnetic circuit, what we have seen, if we excite such a magnetic circuit on the primary winding with a square wave voltage, what kind of flux will be set up in the core is a question which we are interested in. When we excite the primary winding with a square wave voltage, what we see here, which has a certain period Ts and which has the shape of a square wave and which has a magnitude of V, in such a situation, we would like to understand what will be the flux in the core. The relationship between the flux and the voltage is V is N d phi by dt, or we can say that flux is the integral of voltage divided by the number of turns. If you want to get flux from this equation, this has to be integrated on both sides. So, we might say that the flux in the core will be an integral of the voltage to some scale, scaling factor being the number of turns. This property can also be seen graphically here. If a square wave voltage is applied to the winding, the integral of a square wave is nothing but a triangular wave. When the voltage applied to the winding is constant, and if that constant is integrated, you will get flux. So, you get a flux which is a triangular kind of flux. Whenever a positive voltage is applied to the primary, the core in the flux in the core is increasing linearly to reach some maximum value in the positive direction, and when the voltage reverses polarity and becomes negative, the core flux starts decreasing linearly and goes towards the negative maximum, and this goes on. So, under steady state, when a square wave voltage is applied to the transformer primary voltage, the core flux, the flux in the core will be a triangular shaped waveform. And here we have taken the frequency of the voltage excitation to be 1 over the period, 1 by Ts is the frequency. And assuming symmetry in the flux, we might say that flux is swinging symmetrically between minus phi m to plus phi m under steady state situation. So, with a square wave excitation on the primary voltage, the flux waveform will be a triangular shape. Okay. Supposing if we give a quasi square wave is slightly different from a square wave. In the half period, for a certain section, for a certain duration, the voltage is full V, and for some duration the voltage is 0. Then in the negative half, for certain part of the negative cycle, the full voltage minus V is applied, and for a short duration it is 0. So, this 0 periods again will be symmetrical, and you will see that during positive half, a plus voltage is applied for certain fraction of the positive half cycle, and during negative half, for the same fraction, a negative voltage is applied to the primary winding. By doing the integration on the graphical shapes here, you will see that during the time plus voltage is applied, flux is constantly increasing, and during that small duration when the voltage is 0, flux remains constant, because when the applied voltage is 0, integral of d phi by dt is integral of 0, which will be a constant quantity. And then again, when negative voltage is applied, flux starts decreasing and it keeps all the way down to some negative maximum, and during the dwell period here, during the 0 period here, the flux remains again constant, and instead of a triangle wave, we have a kind of a trapezoidal waveform, that is because of the 0 duration in both positive half cycle and negative half cycle. Here also the flux is swinging symmetrically between some minus maximum and plus maximum, and there is a small dwell time. On account of that, the flux waveform is not a triangle, but it is a trapezoidal waveform. Okay. Now, if we wish to find out the design equations for the transformers, it is possible to extend, possible to see these quantitative relationships and relate them to the various geometrical properties of the magnetic circuit. So, V is N into d phi by dt, and change in or this slope is d phi by dt, and because it is a straight line, we can take it as maximum flux minus minimum flux divided by the duration, which is half of Ts. So, this relationship tells that the voltage is now 4 times Bm AC. This is the total flux, maximum flux density multiplied by the core area, and this Ts is 1 by Fs, and if we substitute those relationships, we find that the voltage is N times 4 times maximum flux, core area and frequency. V1 will be the same relationship with N1 and V2 will be N2 times 4 times Bm times AC times Fs. So, I am writing both of them in a simple relationship as V1 is 4 times N1 Bm AC into Fs and V2 is 4 times N2 Bm AC into Fs. The important point here is the core area of the transformer is a function of the voltage and the frequency. V1 is AC and Fs, all other quantities are fixed number of turns for the winding, and the property of the magnetic material is maximum flux density is Bm. So, you would say that V1 is proportional to AC and proportional to Fs, or we could say that AC is directly proportional to V1 and inversely proportional to Fs, and this is the reason many times when you want to excite a transformer at constant flux, it is necessary to maintain the relationship of V by F as constant. You would have come across in many places V by F constant excitation of transformer that relates to constant flux operation of a transformer. The important point is core area is now a function of voltage and frequency. Now, if you look at the window area, this is a second relationship. We see that the total window area accommodates the primary number of turns multiplied by the cross section and secondary number of times multiplied by the cross section to a fraction of the window area. We can say that N1 times A1, that is primary number of turns multiplied by A1 and secondary number of times multiplied by A2 is equal to a fraction of the window area, or AW, the window area that we write here is a function of the conductor size and the number of turns. Okay. And the conductor size can be replaced by whatever is the RMS current divided by the maximum current density allowable for the material. For copper, it is about 3 ampere per millimeter square. For aluminum, it may be about 1.5 ampere per millimeter square. For some other material, it could be something different. So, we might say that this N1 times I1 by J is the primary area of cross section, N2 times secondary area of cross section is a fraction of the window area. So, AW or the window area is a function of the RMS currents. Now, if we combine these equations, design equations, where the total number of turns multiplied by the cross sectional area of each of the turns is related to the window area and the voltage of excitation is related to the core area and frequency, and if these two equations are combined together, we get the most important design equation for a transformer, which is called the area product equation. The area product of the core area multiplied by the window area, the area which accommodates the flux and the area which accommodates the current. This product, the unit of this will be meter power 4 or millimeter power 4, is the product of V1 and I1 or the volt ampere rating of the transformer divided by several quantities: the window space factor, maximum flux density for the core material, the maximum current density for the conducting material and the frequency of operation. So, we see that the core has to be bigger if you want to transfer large power V into I, and the core also is inversely proportional to the window space factor, inversely proportional to the flux density of the core, inversely proportional to the current density of the core, inversely proportional to frequency. This is an important observation. You can see that because Fs is in the denominator, if you build a transformer for a certain frequency, if the frequency becomes double, the same transformer can be used for nearly double the volt ampere rating. This is one of the motivations to process power at high frequency, so that all the magnetic elements will be smaller in size. The popular geometries of transformers are E geometry, and notice that there is a very low reluctance in the gap, because there is no air gap in that. The reluctance in the magnetic circuit is practically 0. On account of that, magnetizing inductance of the transformer will be practically infinity. Ideally, the transformer does not draw any magnetizing current to set up a flux, or the magnetizing inductance of a transformer will be infinity. We will see that in a few moments how to evaluate those quantities. So, we see here that the magnetizing inductance seen from the primary is N1 square by the reluctance of the magnetic circuit. In the earlier lecture, we had seen that in an electromagnetic circuit, N square by reluctance is the inductance of the winding. The primary has N1 turns and secondary has N2 turns, but the magnetic circuit is common for both primary and secondary. So, it is possible to find out the magnetizing inductance and express it as a primary magnetizing inductance or a secondary magnetizing inductance. It is possible to magnetize the core either from the primary or from the secondary. In each case, the appropriate magnetizing inductance will be applicable. On account of this low reluctance magnetic path, the magnetic inductance is really infinity. So, ideally, it will not draw any current to magnetize the core, or if you draw a finite amount of current, the flux, magnetic flux and the magnetic energy storage is practically, energy stored in the transformer is practically 0. This is one of the points that we have seen. So, what I have shown here is one particular type of core called ETD core. So, several of them are available in this family, 29, 34 and so on. So, all of them I have arranged in a certain ascending order, where the core area in millimeter square and the window area in millimeter square and the product of AC AW in millimeter power 4 are organized like this. For example, if we open the magnetizing the data sheet of this type of cores, this is ETD 29, 16, 10. Let me expand the size. Okay. So, you can see that this core has a shape of E, the front view and the top view, and this is a central post which is around which the winding is organized, and these are the two side limbs, and we put two such cores, another E inverted and put on top of that will make the complete magnetic circuit, and in the central limb is the primary and secondary wound, and these are the side limbs and the dimensions are given here. You will see that the central limb has 9.8 diameter circular cross section, and this has a cross sectional area of about 76 millimeter square. And you can see that the window consists of two such things, and the dimension on this side and the dimension on this, the product of that is the window area, and these quantities are expressed here as 76 millimeter square of core area and 128 millimeter square of window area. The product of that is 9728 millimeter power 4. Now, if we have such core data available for any particular design, it is possible to select a suitable core. By making a sample design, we will be able to understand the process. There are several other geometries, we will come back to that a little later. Let us look at a sample design where these core selections are worked out. This is a design where V1 is 48 volts, primary has 48 volts, secondary has 400 volts and secondary current is 3 amperes. Total secondary power is about 1200 watts, 400 into 3, 1200 watts, and it is used for a high frequency application, 50 kilohertz frequency, and let us assume that this is a square wave operation. So, in such a situation, we had seen that ACAW is related to the V into I product divided by 2 times KW times BM times the current density and frequency. If all these numbers are put, what you get here is 57,142 millimeter power 4. Now, if we go back in our core, the core size is set in the ascending order of area product. So, 57 is more than this 48 and less than this 72,000. So, we could select ETD49 as a suitable core for this application. For this 57,000, we could select a core which has an area product which is more than the required 57,000 millimeter power 4. Such a core has an area of core AC to 211 millimeter square and window area of 343 millimeter square, and the product is 72,000, which is more than what we need. Now, this core has been selected 49, 25, 16, and the dimensions are mentioned here. You can see that it has a area of 211 millimeter square, and the other dimensions are central post of 16.7, and the window height for half of this window height is 17.7, and so on, and end to end from this end to this end is about 48.5. In fact, that is the number which is given in the core as the first quantity. ETD 49 refers to the full width of the core, and this is made up of N67 material. It is available, as we see, on different types of materials, and we have selected N67 material. It is available as N87, N67, which are capable of having different types of losses on magnetization, and this can be used at a 0.2 Tesla at 100 kilohertz. The N27 is suitable up to 25 kilohertz. N87 can go to 100 kilohertz, but with less loss compared to the N67, and in this particular design we have selected N67 material. The next part in the design is to find out the number of turns. Number of turns, it is very easy to calculate. It is related to voltage divided by 4 Bm ACFS. We know now the area of cross section for the selected core, which is 211 millimeter square, and Bm is 0.2 Tesla or 200 millitesla. All other quantities 50,000 is the frequency. So, the number of turns for the primary, when you put 48 volts, is 6 turns, and when this is replaced by 400 volts, that will give you the secondary turns, which is 47 turns. The next selection is how big should be the size of each of these conductors, and this is again very simple to calculate, because the cross section of the conductor has to support the current. In this particular case, secondary carries a current of 3 amperes, and if we use a current density of 3 ampere per millimeter square, the secondary cross section of conductor will be 1 millimeter square. Primary cross section of conductor will be 8.33 millimeter square. This has a current of 25 amperes divided by 3 amperes, roughly 8.33 millimeter square. There is one other important point to see. Whenever we process power at high frequency, the standard conducting material is not capable of carrying current across its entire cross section, and this particular property is known as skin effect. As you go to higher and higher frequency, the current is limited to the surface of the conductor, and it does not flow through the entire cross section. It is as if only the skin of the conductor is carrying the current, and the core of the conductor is not carrying the current, and this effect is known as skin effect, and there is a mathematical relationship between the skin depth and the various properties of the conducting material. Mu is the permeability of the conducting material, which is normally 4 pi 10 power minus 7 Henry per meter. Sigma is the conductivity of the conducting material. For copper, it is 59.6 10 power 6 per ohm meter, and F is the frequency at which the conductor is used. From this, you can see that if the frequency is infinity, then the skin depth becomes 0. The conductor is not capable of carrying any current inside the section. All the current will go through the surface only. At other frequencies determined by the skin depth, the current will be limited to a portion of the cross section. For our application at 50 kilohertz for copper with this permeability and conductivity, the skin depth is 0.29 millimeter, and this is equivalent to 0.26 millimeter square of cross section. See, 0.29 millimeter skin depth, you can approach the skin from either side. So, that this will mean I can use a conductor whose diameter is double this 0.58 millimeter, and such a conductor will have a cross sectional area of 0.26 millimeter square, and this cross sectional area is equivalent to an appropriate standard wire gauge for that. So, if we limit the size of the wire to that wire gauge, 24 standard wire gauge, for our 1 millimeter square, it is necessary to use 4 wires in parallel in order to make the total cross section, because each conductor has only 0.26 millimeter square cross section. For the primary, which carries a current of about 25 amperes, we have to have 32 wires in parallel. Such parallel connection of wires are also called Litz wires. Litz wires are isolated sectionalized wires, several of them in parallel, in order to overcome the skin effect. So, the secondary and primary will be organized 24 SWG wire, 4 in parallel for the secondary winding, which is 3 amperes, and 24 SWG wire, 32 wires in parallel for the primary, which carries a current of about 25 amperes. The parasitic resistance, see, the conductor has an inductance which is responsible for the flux, and the flux is responsible for transferring the energy from primary to secondary. But these conductors also have a finite conductivity, and because of that it has a resistance. The primary winding has a resistance, secondary winding has a resistance. This is related to the mean length of the turn and number of turns, and then the property of resistivity and cross section of the wire. And in this particular example, if we calculate, it turns out to be primary resistance is 10 micro ohms and secondary resistance is 629 micro ohm. This is a parasitic resistance. Ideally, a transformer should not have any resistance. On account of this resistance, the 25 amperes of primary current going through this 10 micro ohm will result in a certain loss. Ideally, transformer neither stores energy nor loses energy, but because of this primary resistance and secondary resistance, there will be some loss. Okay. Let us look at the magnetization part. We assume that the permeability of this material will be infinity. That is really not true, because most magnetic materials have a finite permeability. It may be 1000 or 2000, but it is not infinity. On account of that, it is possible that this transformer, I think before the permeability, let us come to core loss. See, this magnetic material is being or flux is being set up to the level of 0.2 Tesla at 50,000 cycles per second. On account of that, the material has a magnetization loss which is known as the core loss. This core loss in materials consists of eddy current loss and hysteresis loss, but in the high frequency cores, the eddy current loss is negligible because the material has practically very high resistivity, and only the hysteresis loss is present, and that is given in the data sheet. As we see here in the data sheet, it is given as for N67 material at 200 millitesla at 100 kilohertz, it is about 15.5 watts per core set, and if we operate at 50 kilohertz, this loss will be 1/2 of that, because hysteresis loss is proportional to the frequency. When operating at 50 kilohertz, the loss will be about 70, 1/2 of this, which is 7.75 watts. And this can be represented in the equivalent circuit with an appropriate resistance. We will see that a little later. The magnetizing inductance of the transformer ideally has to be infinity, so that there is no stored energy in the core. But in a real transformer, there is a finite magnetizing inductance, and on account of this, there is a magnetization current, magnetization flux, and so on. In this particular core, the core length is 114 mm, the core area is 211 mm square, and the relative permeability of the core we had seen for the from the data sheet, we can see that the permeability, relative permeability is 1590 for N67 material. Mu r is 1590 and the reluctance is given by L divided by A mu r mu naught, and that quantity is 270,405, and per Henry is the unit for reluctance, and the primary inductance is N square, 6 turns for the primary, 6 square divided by this. Secondary inductance is 47 square divided by this quantity. So, that is 0.133 millihenry, and secondary inductance is 8.17 millihenry. Ideally, this should have been infinity, but in practice this is a finite quantity. Now, because of this magnetizing inductance, when we apply the given voltage in this case, there is a magnetizing current which is a finite quantity, not 0, and this is related by the peak current is 48 volts divided by the magnetizing inductance and multiplied by the duration of this. When we are switching it at about 50 kilohertz, Ts is 100 microsecond, Ts is 20 microsecond, Ts by 2 is 10 microsecond, the voltage is 48, and the slope of this is Im peak, both minus and plus, is 1/2 of that. 48 by 0.133 into 10 micro is about 1.8 amperes. The rated current for this transformer was 25 amperes, and you can see that magnetizing current is a small fraction, less than about 1/10 of that. Magnetizing current peak is very much less than the primary current, which is about 25 amperes. In good designs, this will always be true. In very good designs, this inequality will be even better satisfied. The stored energy in an ideal inductor, ideal transformer was 0, but because of this magnetizing current, there is a finite stored energy 1/2 of Lm Im square, and that is 0.22 millijoule. This is another non-ideality. Ideally, this should have been 0, but in a real transformer, the stored energy is a finite quantity, but it is a small quantity. The second important non-ideality in the transformer is the leakage field in the window area. Ideally, the field, magnetic field has to be only in the core and not in anywhere outside the core. That will be true if the permeability of the magnetic material is perfect, is infinity. There will be no leakage field in the air, in the outside the core or in the window. But in a real transformer where the permeability is not infinity, there will be some leakage field in the core, and that leakage field is not linked by both the primary and the secondary. It is only partially linked by the primary or the secondary, and this is a non-ideality in most transformers, and it is possible to evaluate the quantity through the geometrical properties of the core. In this particular situation, the blue cross section is the primary winding, and the red cross section is the secondary winding, and the window is seen here as a rectangular window, and apart from the flux which goes in the core, there will also be a leakage flux shown as phi L, both in this window and also this window. And this phi L, if we can find out, it is possible to find out what is the leakage inductance. The method to find out this phi L is to identify or understand the magnetic circuit here. This is a purely non-magnetic material. Window is a completely non-magnetic material, copper conductors and air, and the top portion is the highly magnetic material, bottom portion is a highly magnetic material, but the entire window is a non-magnetic material. So, it is possible to model this in a very simple way, that a highly magnetic material at the top and a highly magnetic material at the bottom, and the magnetization ampere turns because of the red winding or primary winding, and the magnetization magnetic turns are the other winding, which is the secondary, which is a increasing ampere turns, because as the current is building up, any line that you take from here is enclosing the current that is to the right hand side of that. So, you might say that at a distance x from the left hand side, if you consider a vertical line, it is possible to find h of x along this vertical line. This will be the total ampere turns divided by this h, because magnetizing intensity is ampere turn divided by h, and because it is linearly increasing from 0 to N1I1 and dropping to 0 at the end of the window, this relationship at any cross section x, the magnetizing field h is the ampere turns multiplied by this ratio x by b. At b, it is maximum N1I1, at any other distance x, it is N1I1 into x by b, that is the ampere turns, that divided by the leakage path length h is the magnetizing field, and the flux density is the field multiplied by mu. If this is h, mu into h is the field, and the inductance can be simply calculated by volume integrating h square in this volume of this window. If you integrate h square and multiply by this mu naught by I square, that will be the leakage inductance, and the volume that you have to integrate is the volume of this complete window h multiplied by w, which is this width, and then dx, the small incremental distance that we have considered is dx, and there are two such windows on this side and the right hand side. So, you get 2 h w dx is the volume that we want to integrate this, and if this integration is carried out, and we find that for this particular example, the leakage inductance is 0.07 microhenry, and this has to be compared with magnetizing inductance, which is 133 microhenry. The magnetizing inductance will be very much higher compared to leakage inductance, and we can also see for this particular situation of 48 volts and 25 amperes and 50,000 cycles per second, it is possible to find out what is the normal inductance. Normal inductance is the same as the rated current into omega L is equal to rated voltage. That inductance is 6.1 microhenry, and you can see that leakage inductance will be a very small fraction of per unit inductance, and magnetizing inductance will be a very large multiple of per unit inductance. If we, as we go to the ideal situation, leakage inductance will go to 0, magnetizing inductance will go to infinity, and per unit inductance is related by V divided by omega times IL. In this situation, you can see that the leakage inductance is almost 100 times less than the per unit inductance, and the magnetizing inductance is about 20 times more than the per unit inductance, which is a very good situation. The transformer can be now modeled with all these non-idealities. We saw that about 10 micro ohm and 629 micro ohm here, and leakage inductance of about 0.07 microhenry, and a similar kind of secondary side leakage inductance, which will be this same inductance multiplied by the square of the number of turns ratio, and the magnetizing inductance of 133 microhenry, and the loss resistance which we had seen from the core loss, we converted it into an equivalent resistance of something like 270 ohms or so. This is the circuit model of the transformer. Now, whatever we had ideally designed, that transformer is there, but there are several non-idealities: magnetization, leakage, conduction. But this is our ideal transformer. All non-idealities will be normally very small compared to the ideal properties which we designed for. How do you measure these quantities? Measurement of these circuit parameters is very simple. All of you must have studied in the transformer theory that by simply conducting an open circuit test and a short circuit test, it is possible to evaluate all these quantities in a transformer. If you short circuit the secondary and apply a small voltage and pass rated current and measure the power that is given to the transformer, and in a similar way open circuit the secondary, give the rated voltage to the primary, find out what is the current drawn and power supplied to the primary side, it is possible to separate all these quantities, and resistance of the primary and secondary can be measured with appropriate DC voltage and DC current method. It is a standard method of making suitable tests, DC resistance measurements, and then an open circuit test and a short circuit test. This is the standard method of evaluating the parameters of a transformer, and after having designed, evaluating the parameters will completely verify that our design method is good. So, what we have seen in this section is about the transformers. What is a basic principle, how the primary and secondary are linking to each other through the magnetic circuit in between, what are the various relationships of the electrical quantities as well as the magnetic quantities, how does one design a transformer starting with the voltage, current, frequency ratings, and having designed the ideal transformer, how do you go about finding out all the non-ideal features of the transformer, such as the primary resistance, secondary resistance, leakage inductance, primary leakage inductance, secondary leakage inductance, magnetizing inductance, the core loss, and so on. This could be a good starting exercise to understand about transformers, and later on as we get to know about power converters, we will design very specific designs getting into even more details of that. Thank you very much.